Hello, hello everyone, Namaste. I am Rohan Banjarkar, and in this video, we will further dive into the matrix method of OLS. In this video, we will deal with the blue property of OLS by matrix method, and secondly, we will dive into the variance covariance matrix of disturbance term, that is error term, and we will further discuss about the variance covariance matrix of the beta coefficients. And finally, in the next video, we will deal with multiple linear regression by deviation method. So I will add a new page and let's keep its name as further dive into matrix method. So first of all, we will do or we will discuss about some of the properties of OLS estimators in the matrix method. So for it, I will write properties of the OLS estimators. And the first basic property is that let's say that y equals to alpha plus beta x plus e. The first property is that summation xe equals to 0. It means that x must be independent of e. And how can it show it in the matrix method? Since we have learned that beta hat equals to x transpose x inverse x transpose y. This is the value that we derived for the beta hat. Let's see it. We have already derived it, and you can see it in my previous video. So the with this we can further go step with x transpose x times beta hat equals to x transpose y. Since beta hat equals to, this is the formula we derived, then we can go back to this step. After going back to this step, we will simply reduce the value of y. X transpose its y is simply x beta hat plus e. So let's recall y equals to x beta plus e is the functional form or the matrix form of the multiple linear regression or the linear regression model. So for it, I will simply do the further calculations, and x beta hat plus, let's open it, x e. So now these two terms are same, or they are identical. So I can write that x transpose e equals to x transpose x beta hat minus x transpose x beta hat. So this part will be of the null matrix. So x transpose e equals to 0. This is the and this is the basic property that every OLS estimator must satisfy. And this also means that it's simply summation xe equals to 0. So following this, we will have the other basic properties, such as number 1, it's the observed value of x are uncorrelated with the residuals. The observed value of x are uncorrelated with the residues. What does this mean? It means that x transpose E equals to 0, that we have already proved. It means that it means that the independent variables are not correlated with error term. This further means that this further means that this further means that there is no any missing variable, no any missing variable in the model that is capable of affecting the independent variables. This means that we are making a model. Let's say C is the function of, we only call it as y. C is the constant expenses and y is income. And let's make it model alpha plus beta y plus e. And in the error term, there are all other variables that we haven't considered in our model. So there might be the variable that might affect the income. That may be education level, or that may be ability, or that may be even gender, and so on. And these variables are actually influencing our independent variable. So these variables are missing, and they are called omitted variables. They are called omitted variables. And these variables may cause a serious problem in our OLS estimation. And the second property is property number 2, is that the sum of residuals is 0. The sum of residuals is 0. It means that it simply means that summation ei equals to 0, or in matrix form sorry it in matrix summation ei equals to 0. And number 3, the sample mean of residuals is 0. The sample mean of residuals is 0. And this is obvious. This is obvious because summation ei is itself 0. So e bar equals to summation ei by n, which is equals to 0. And number 4, the regression hyperplane passes through the mean of observed values. Mean of observed values. What does it mean? It means that every line passes through x bar and y bar. Let's make it proof. Since we call e bar equals to 0, e equals to y minus x beta hat, and let's divide this by n, by n, by n, by n. It means that it will be simply e bar, and it will be y minus x bar beta hat. And since we know that e bar equals 0, and y bar equals to x bar beta hat, this shows that the regression line will pass through y bar and x bar. The predicted value of y are uncorrelated with the residuals. The final property, the predicted value of y are uncorrelated with error term. What does it mean? It simply means that the value we predict for y or y hat, it must not be influenced by the error term. That is, y hat equals to its x beta. This gives equals to x beta, and y hat times e equals to x beta times e. And if we take the transpose of y hat, it will simply be x beta transpose e, and y hat transpose e equals to, by using the property of matrix, it will be x transpose e. And from it we know that this term, this is simply 0, so where e equals to 0. So through this we have proved the properties of OLS, and these are the basic properties that every OLS estimator must satisfy. So now let's move towards the Gauss-Markov assumption. We will head towards the Gauss-Markov assumption. It also means that the blue property assumption. Gauss-Markov assumption. What does it mean? Number one, it must be linear. One is linear. Linear means that y equals to x beta plus e, and this must be linear. Second is x is an n times k matrix of full rank. What does the full rank mean? In simple sense, a matrix is of full rank if its determinant is not equal to 0. It means that every column vector in matrix is linearly independent. So if a matrix is a full rank, then we can also say that there is no problem of perfect multicollinearity. So these are the main three main requirements or the conclusions from the full rank concept. The first concept is that a matrix is of full rank if its determinant is not equal to 0, or the matrix is not singular. It means that every mm, column vector of matrix is linearly independent. Means that every column is unique, and the last is there is no problem of perfect multicollinearity. If the matrix is a full rank, then we can conclude that the mm, the problem the the matrix is free from, or the equation is free from the problem of multicollinearity. And the third property is expected value of error term given x equals to 0. This is the very fundamental assumptions, or the conditional mean value of the disturbance term is 0. And 4, it means that expected value of error term with respect to its transpose is equals to sigma square I. This means that constant variance. So now let's derive the variance covariance matrix of the disturbance term. Expected value of error term times the transpose of error term given x is equals to, let's make its matrix. It will be simply the matrix of error term is e1 e2 dot 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 en, and its transpose will simply be the row vector e1 e2 dot 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 en. And if we multiply it is a matrix of n minus n times 1, and it's n times 1 times n, so the matrix will be of dimension n times n. So simply it will be expectation sign will take exponential sign, and it will be e1 square dot 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 dot, it will be e1 en. And similarly the second case is the second will be e1 e2 dot 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 dot, and the last will be e1 en dot dot dot, sorry, and the last will be en e1 dot 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 dot, and it will be en square. And let's open the sign of expression, and it will be simply, here is x given x, it's a conditional value, so it's given x, and let's open it. It will be expected value of e1 square given x dot 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 dot, expected value of e1 en given x, and dot 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 en e1 given x dot 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 dot, and en square given x. And since we know that the variance is constant, so it's sigma square, and it's all 0 0 dot 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 0, and it's sigma square 0 dot dot dot, it's sigma square, all other are 0 0 dot 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 0. And if we take the sigma from here, it's sigma, its identity matrix of n times n, 0 0 1 0, and it will be 0 dot 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 1, it's n times n matrix, and sigma square equals to exponent value of ei square, sigma square equals to ei square given x. So it will be sigma square I, and this is the variance covariance matrix of the error term that we have just derived. And following it, the last property is, I think we have in number 4. Number 5 is that, number 5 property is that error term given x is normally distributed with mean 0 and variance sigma square I. This is the property for the normality condition. Normality, but this condition is just the sufficient condition, not the necessary condition. Thank you, and we will cover the Gauss-Markov theorem in the next video.